Picture, for a moment, the edge of everything you call home. Not the moon, not the planets, not even the icy ring past Neptune, but far beyond all of it, a shell of frozen worlds so enormous it reaches a third of the way to the next star. For 75 years, that shell existed only inside equations. We could not see it, could not photograph it, could only reason that it had to be there, because the comets had to come from somewhere. And then we built a telescope sensitive enough to look into the beginning of the universe, and we turned it, almost as an afterthought, toward our own frozen frontier. What it found in that cold and silent dark was not the empty graveyard we expected. So what exactly has been waiting out there, surrounding us on every side for longer than the Earth has existed? Settle in and get comfortable. Subscribe if you have not already, and stay with me tonight, because the closer we listen to what is falling out of that dark, the less empty it turns out to be. Let's get into it. Part 1. A place that lived only in equations. There is a place that surrounds you right now, in every direction you could possibly point, and until very recently no one had ever seen it. It has no surface you could stand on as a single object, no edge you could photograph, no shape you could draw from life. For most of the time, human beings have been looking up at the sky. This place did not exist at all. Then, for a single human lifetime, it existed only as a line of reasoning, a conclusion that had to be true even though nothing could confirm it. And now, in the last few years, something has changed. We have finally built an instrument patient enough and sensitive enough to turn toward that frozen frontier and begin very slowly to hear it answer back. The place is called the Oort Cloud, and it is the outermost region of our own solar system. Picture everything you usually think of as space close to home. Picture the sun, and the 8 planets, and the familiar band of asteroids, and far out past Neptune the scattered ring of icy worlds we call the Kuiper Belt. Now, imagine all of that shrinking to a tiny bright knot at the very centre of something thousands of times larger. Wrapped around that knot like the faint shell of a soap bubble around a single grain of sand is a sphere of frozen bodies so enormous that it reaches a meaningful fraction of the way to the next star. That shell is the Oort Cloud. It begins somewhere around 2,000 times the distance between the Earth and the Sun, and it stretches outward to perhaps 100,000 times that distance, and by some estimates twice as far again, until you are talking about a boundary that sits more than 3 light-years from home, a third of the way to the nearest star to our own. You have never seen a picture of it, and here is the part that matters. You never will. No telescope that exists, and no telescope anyone has seriously proposed, can take a photograph of the Oort Cloud as a whole. The objects out there are too small, too cold, and too far apart, scattered so thinly through such an immense volume that the cloud is, for all practical purposes, invisible. And yet we're now more certain than we have ever been that it is real, that it is full, and that it has been quietly shaping the sky above your head for as long as there has been a sky. To understand how strange that is, you have to understand how we got here, because for 75 years the Oort Cloud was the most important place in our solar system that no human eye had ever observed. It was discovered, if you can call it that, not through a lens but through a kind of detective work. A man sat with a list of comets and the paths they traced, and from the pattern of where they came from, he reasoned an entire world into being. He could not see it. He could not measure it directly. He could only show that it had to be there, because the things that fell out of it had to come from somewhere. For 3/4 of a century after that, the cloud lived almost entirely inside equations. It was a place you could calculate but never visit, a guess with a name. That is the journey I want to take you on tonight, and I want to be honest with you about the shape of it before we begin, because it is not the story you might expect. This is not the story of a telescope taking a beautiful photograph and revealing a hidden world of ice. There is no such photograph, and there never will be. This is something stranger and in the end more interesting. It is the story of how we learn to study a place we cannot see by listening to the rare messengers that fall out of it, one at a time, across thousands of years. It is the story of how the most distant region of our own solar system stopped being a guess and started becoming a place. And as you settle in, I want to plant one idea in your mind gently, so that we can return to it later when it has more weight. For a very long time, we thought of the space around our sun as essentially empty. A little sunlight, a few planets, and then nothing. A clean and silent void reaching out to the stars. What the last few years have begun to suggest is that this picture is wrong in a way that is almost difficult to absorb. The dark around us is not empty. It is full of structure, full of history, full of objects that have been waiting in the cold for the moment something would finally look hard enough to find them. By the time we're finished tonight, I want you to feel the strange truth of a single sentence, the one written across the thumbnail that brought you here. We're not alone in our own backyard. For now, hold that lightly. Because before we can talk about what is out there, we have to talk about how anyone ever suspected it was there in the first place, when not one person had laid eyes on a single piece of it. We have to go back to the middle of the last century, to a quiet office in the Netherlands, and to a scientist looking at the loneliest objects in the sky and noticing something that no one else had quite put together. The comets are where this begins, and the comets are where it will keep returning. So let me tell you what a comet actually is before we follow one home. When you picture a comet, you probably picture the tail, that long bright smear across the night that has frightened and amazed people for thousands of years. But the tail is the least of it. The tail is just gas and dust, boiled off a small icy core as it nears the sun and warms, blown back into a glowing banner by the pressure of sunlight. The real object, the thing that matters, is that icy core, often only a few miles across, a dark and frozen lump of ice and rock and ancient chemistry. Most of the time, that core is nowhere near the sun. Most of the time, it is somewhere out in the cold and the dark, moving so slowly along an orbit so enormous that a single trip around the sun can take longer than all of recorded human history. Some comets keep to short, tidy loops, swinging back every few years or few decades from that nearer ring beyond Neptune. But others are different. Others arrive on paths so long and so steep that we may only ever see them once, falling in from somewhere unimaginably far, rounding the sun in a matter of months, and then climbing back out into the dark for thousands or tens of thousands of years before they return, if they ever return at all. These are the long-period comets, and they are the thread we're going to follow. Because every one of them is a visitor from that invisible shell, a single grain of sand falling toward us from a distant beach. And for most of human history, they were the only evidence we had that the beach existed at all. To grasp the scale of what we're talking about, it helps to shrink the familiar solar system down to almost nothing. Picture the orbit of Neptune, the outermost of the major planets, the boundary most of us quietly think of as the edge of everything. On the scale of the Oort Cloud, Neptune's orbit is not even a dot. It sits far inside the inner wall of the cloud, hundreds of times closer to the sun than the place where the great shell even begins. Everything you have ever seen drawn in a diagram of the solar system, every planet, the asteroid belt, even the icy ring beyond Neptune, all of it would fit inside a single bright speck at the very centre, with almost the entire structure being dark and empty space wrapped around that speck. The Oort Cloud is, by a wide margin, the largest thing that belongs to our Sun, and it is the part we have known the least about for the longest time. There is a strange humility in that. We tend to think we have a decent map of our own neighbourhood. We have sent spacecraft to every planet. We have landed on a comet and on worlds beyond Mars. We have photographed the storms of Jupiter and the rings of Saturn in detail that would have stunned astronomers a century ago. And yet the single largest region of our own solar system, the one that holds more individual worlds than everything else combined, has until now been almost completely unknown to us. A blank space on the map labelled only with a name and a rough guess at its size. Imagine drawing a map of your own house and being forced to leave the largest room entirely empty, marked only with the words, "We believe something is in here." And the something, it turns out, is not a little. The current estimates put the number of objects in the Oort Cloud in the trillions, with the total amount of frozen material adding up to somewhere between a few times the mass of the Earth and as much as 100 times it, depending on which model you trust. That is the paradox we're going to keep circling back to tonight, so let me state it plainly now. The cloud is, at the same time, almost perfectly empty and astonishingly full. It is empty in the sense that the objects are so far apart you could stand on one and never see another. It is full in the sense that there is something, somewhere, in nearly every direction, trillions of frozen worlds scattered through a volume so enormous that the human mind has no real handhold on it. Holding both of those truths at once is part of what it means to understand this place. That is the situation we find ourselves in as the story opens. A region of our own solar system, larger than everything else in it combined, that we could only know by waiting. Waiting for one of its residents to be jostled loose and to fall inward, where the warmth could finally make it briefly visible before it vanished again. A patient, almost passive kind of science, listening for messages that arrived once every few thousand years from a place we could only guess at. For 75 years that was the best we could do, and then we built something that changed what the word listening could mean. Part 2. The Man Who Heard a Sphere. In 1950, a Dutch astronomer named Jan Oort sat down with a problem that most people would have walked straight past. He was studying the orbits of long-period comets, those rare visitors that fall in from enormous distances round the sun once and leave. He had a collection of their paths carefully measured, and he started looking for a pattern in where they came from. What he found is one of the quietest, most elegant pieces of reasoning in the history of astronomy, and almost nobody outside of science has ever heard the man's name. Here is what Oort noticed. If the long-period comets had come from the flat plane where the planets orbit, you would expect them to arrive roughly along that plane, like cars merging onto a familiar highway. They did not. They arrived from everywhere. Some came in from far above the plane of the planets, some from far below, some from the left and the right and every angle in between, spread across the whole sky, with no preferred direction at all. And there is really only one shape that throws objects at you evenly from every possible direction. A sphere. A shell completely surrounding the thing at its centre. Then Oort noticed something even more telling. A great many of these comets seemed to be arriving for the very first time, falling in from incredible distances on orbits that had clearly never brought them close to the sun before. They were not regulars, they were strangers, and they were coming from a reservoir so far away that the sun's grip on them was almost gentle, almost nothing. From these two clues, the direction and the distance, Oort reasoned his way to a conclusion that he could not see and could not prove by looking. There had to be an enormous reservoir of icy bodies surrounding the entire solar system in every direction, far beyond the orbit of any planet. A graveyard, you might say, of leftovers from the birth of the planets. Or, in a kinder image, a frozen library of the original materials that built everything we know. Think about what kind of mind it takes to do that. To sit with nothing but a list of where some comets came from, and to conclude from that alone that our solar system is wrapped in a shell of frozen worlds stretching a third of the way to the next star. He was not looking at the cloud. He was looking at the splash marks of the few drops that had fallen out of it, and from the splash marks he described the ocean, and then he had to live with the fact that he would almost certainly never see it confirmed. The objects he was describing were so faint and so far away that the telescopes of his lifetime had no hope of detecting a single one of them sitting out there in place. He had reasoned a world into existence, and then handed it to the future, trusting that someday someone would build the eyes to check his work. The problem, for decade after decade, was exactly that. Nobody could see it. For 70 years, the Oort Cloud remained the most important place in the solar system that no human being had ever observed. And it is worth slowing down to understand why. because the reasons it stayed invisible are the same reasons that finally seeing into it is such a remarkable thing. Start with the cold. Out where these objects live, the sun is not a source of warmth. It is just another point of light, brighter than the other stars but not by much. The temperature of a body drifting in the Oort Cloud hovers only a few degrees above absolute zero, which is the coldest temperature that is physically possible anywhere in this universe, the point at which the motion inside matter itself nearly stops. A surface that cold gives off almost no light of its own. It does not glow in any colour your eye could catch. Whatever faint heat it radiates comes out as infrared light, the kind your eye cannot see at all, and even that signal is so weak it is almost nothing. Then add the size. The individual bodies out there are small, most of them only a few miles across, many far smaller. A few miles of dark ice, billions of miles away, reflecting a sunlight that has thinned almost to darkness by the time it reaches them. Trying to spot one is like trying to see a single lump of coal, unlit from the other side of a continent. Then add the distance, and the distance is the part that breaks the mind a little. The inner edge of the Oort Cloud sits roughly 2,000 times farther from the Sun than the Earth is. In plain numbers, that is something like 186 billion miles just to reach the near edge. The outer edge stretches to something on the order of 9 trillion miles. Let me try to make those numbers mean something, because a number alone is just noise. Imagine you could climb into an ordinary car and drive toward the cloud at 60 miles an hour, without ever stopping for fuel or sleep or anything at all. To reach the inner edge, the near boundary, you would be driving for more than 350,000 years. To cross all the way to the outer edge, you would need over 17 million years of unbroken driving. Our entire species is only a few 100,000 years old. You would run out of human history many times over before you even arrived at the place where the cloud begins. So that was the situation. A region too cold to glow, made of objects too small to catch, spread across distances too enormous to cross, and so thinly populated that even out there in the thick of it, you would likely never see your nearest neighbour. Every reason a place could possibly have to stay hidden, the Oort Cloud had all of them at once, and so astronomers studied it the only way they could, which was to wait. I want you to sit with how strange that method is because we so rarely think about it. For most of a century, the science of the Oort Cloud was, in a real sense, the science of patience. You could not go to the cloud, and you could not look at the cloud. You could only wait for the cloud to send you something. Every few thousand years, give or take, the gentle gravity of a passing star, or the slow tide of the galaxy itself, would reach into that distant shell and nudge one of its frozen residents just slightly off its long, slow orbit. Over the course of millions of years, that tiny nudge would tip the object inward, and it would begin the longest fall imaginable, dropping toward the distant warmth of the sun. And only at the very end of that fall, when it finally came close enough for sunlight to warm its ancient ice and wrap it in a glowing tail, would it become, for a few brief months, something we could actually see. That was the messenger. That was the once in thousands of years letter from a place we could only imagine. And for 75 years, reading those letters was all we had. We could catch a comet, measure its path, watch it brighten and fade, and from that single visitor try to infer something about the immense unseen reservoir it had fallen from. It was honest work and it was patient work and it told us a great deal, but it was always indirect. It was always one drop at a time, with the ocean itself staying perfectly, stubbornly invisible. Here is the thing about a place you can only know by waiting. It stays, in your imagination, a little bit unreal. It never quite becomes a destination, never quite becomes somewhere with its own weather and texture and chemistry. It stays a hypothesis with a name attached, a line in the equations, a thing that has to be true rather than a thing you have touched. For 3 generations of astronomers, that is exactly what the Oort Cloud was, a certainty that never became a place. It is worth dwelling on just how little Oort had to work with, because it sharpens what he accomplished. He did not have a fleet of telescopes feeding him data every night. He did not have computers running simulations of how comets fall. He had a modest list of carefully measured comet orbits, gathered painstakingly over many years, and he had his own reasoning. From that, he did not just guess that comets came from far away. He worked out roughly how far, and roughly how the reservoir had to be shaped, and he even reasoned about how it would be slowly stirred over time. He understood that the bodies at the very outer edge of the cloud are held so loosely by the sun that the gentlest outside influence could tip them loose. A star drifting past at a distance, the slow gravitational pull of the wider galaxy itself, even these faint, far-off forces would be enough, over millions of years, to nudge a distant comet out of its long sleep and start it falling inward. That insight is the quiet engine behind every comet we have ever seen fall from the cloud. The reason a long-period comet appears in our sky at all is that, sometime in the unimaginable past, something out in the dark gave one frozen body the lightest possible push. Not a collision, not a catastrophe, just a whisper of gravity, enough to bend its orbit by a fraction of a degree. And that tiny change, multiplied across millions of years and billions of miles, was enough to send it on the long fall toward the sun. The comet that lights up our sky for a few weeks is the end of a journey that began with a nudge before human beings existed. There is something almost unbearably patient about the science Oort began, and I keep coming back to it. He described a place he would never see confirmed. He laid out, in careful reasoning, the shape of a structure whose individual members would not be directly detected until long after his lifetime. He trusted that the future would build the instruments to check his work, and he was right, but he did not get to watch it happen. That is the quiet bargain that so much of science is built on. You add your piece to a structure you will not live to see finished, and you trust that someone someday will lay the next stone. Tonight, we are standing on a part of that structure that Oort could only point toward in the dark. What it needed was not a faster spacecraft or a longer wait. No spacecraft we have ever built will reach the inner edge of that cloud for tens of thousands of years. What it needed was a new way of listening, an instrument so sensitive that when one of those frozen messengers fell inward, we could do far more than watch it glow. We could read it. We could take the faint light coming off it and pull that light apart into its ingredients, and from the ingredients learn what the messenger was made of, and from what it was made of, finally start to learn something true about the unseen place it came from. That instrument was not designed for any of this. It was built to look in the opposite direction, at the very edge of the universe, and the very dawn of time. But the same power that let it see the beginning of everything turned out to be exactly what we needed to see into our own backyard. Part 3. The telescope that was not built for this. The James Webb Space Telescope was never meant to study comets. When you read the documents that justified building it, the documents that argued for more than 2 decades of work and many billions of dollars, you will not find the Oort Cloud anywhere near the top of the list. Webb was built to look at the earliest galaxies in the universe, the first faint smudges of light that formed after the Big Bang. It was built to peer inside the clouds of gas and dust where new stars are being born, places ordinary telescopes cannot see into. And it was built to study the atmospheres of planets orbiting other stars, to read the air of distant worlds for the chemistry of their skies. Those were the missions. Those were the reasons it exists. Looking at a chunk of ice in our own solar system was, at best, an afterthought. To do those things, the engineers had to build an instrument of almost absurd sensitivity, and the way they did it is the key to this entire story. So let me walk you through it slowly. Webb's main mirror spans more than 21 feet across, far too large to fit inside any rocket in one piece, so it was built as 18 separate gold-coated segments that folded up like a piece of origami for launch, and then unfolded perfectly once it reached space. A larger mirror gathers more light, and gathering more light is how you see things that are unimaginably faint. But the size of the mirror is not the clever part. The clever part is the cold. Webb is an infrared telescope. It is built to see heat, the long, slow wavelengths of light that warm objects give off. the light your own body is glowing in right now, even in a dark room, the light your eyes cannot detect. And there is a serious problem buried in that idea. If you build a telescope to detect heat, then the warmth of the telescope itself becomes a blinding glare. Its own heat would drown out every faint signal it was trying to catch, like trying to photograph a candle while standing inside a furnace. So the engineers did something extreme. They gave Webb an enormous sunshield, 5 layers, each one about the size of a tennis court, to block the heat of the sun. And behind that shield, they let the telescope's detectors cool to within a few degrees of absolute zero, almost exactly as cold as the frozen bodies in the Oort Cloud themselves. Only by becoming nearly as cold as the surrounding dark could the telescope stop being blinded by itself. It launched on the 25th of December 2021 and travelled about 1 million miles from Earth to a quiet point in space where it could keep its back to the sun and stare out into the dark. And then it began to do exactly what it was built for. It looked at galaxies so far away that their light had been travelling toward us for more than 13 billion years. It read the atmospheres of planets hundreds of light years from here, detecting the chemistry of their air from across that enormous gulf. It performed beautifully, better than its builders had dared to hope. But here is the thing about an instrument that's sensitive. Sensitivity does not care which direction you point it. The same detectors that can register the faint thermal glow of a planet 700 light-years away can register the faint thermal glow of a chunk of ice drifting much closer to home. The same spectrograph that can split the light of a distant world into its chemical ingredients can split the light coming off a comet. The telescope built to read the air of alien planets turned out to be, almost by accident, the most powerful tool ever made for reading the chemistry of our own solar system's frozen edge. The difference, the thing that made this exciting, was that our own backyard was a place we had barely begun to map. Now, I have to be careful and honest with you here, because the popular version of this story gets one important thing wrong, and I do not want you walking away with the wrong picture. You may have seen this story told as though Webb pointed its mirror out at the Oort Cloud and took its measure directly, as though it stared into that distant shell and saw what was there. That is not what happened, and it could not happen. Webb cannot see the Oort Cloud any more than any other telescope can. What Webb can do, and what it has actually done, is something more subtle and I think more beautiful. When one of those frozen messengers falls inward, when a long-period comet comes close enough to study, Webb can turn toward it and read it in a way nothing before could. It can take that single grain of sand from the distant beach and tell us, in extraordinary detail, what the grain is made of. And from enough grains, patiently gathered, you can begin to describe the beach you will never walk on. So the method has not actually changed since Jan Oort's time. We are still studying the Oort Cloud by waiting for it to send us something. We are still reading the rare letters that fall inward across thousands of years. What has changed is what we can do when a letter arrives. For 75 years, when a comet came, we could watch it. We could measure its path and its brightness and the shape of its tail. Now, when a comet comes, we can do something closer to listening. We can take it apart, not physically, but in light, and hear what it has to say about the place it came from. A telescope built to hear the first voices in the universe turned out to be the instrument that finally let us hear the voices falling out of our own dark. And the way it listens is worth understanding, because it is the engine of everything that follows. When sunlight warms a comet, gases lift off its frozen core and form a glowing cloud around it. Each kind of gas, each molecule, glows in its own exact set of colours, a fingerprint as unique as a signature. Water has its signature, carbon dioxide has its own. Carbon monoxide, methane, the carbon-bearing molecules that are the building blocks of organic chemistry, each of them announces itself in a specific pattern of light. Webb's spectrograph takes the faint light from the comet and spreads it out, the way a prism spreads sunlight into a rainbow, and in that spread-out light the fingerprints appear. From across more than 1 billion miles without ever touching the object, Webb can tell you not just that a comet is there, but what it is made of, molecule by molecule. It can read a chemistry record older than anything in the inner solar system, written in a language of light. I keep using the word listening, and I want to defend it, because it is not just a pretty metaphor. It points at a real and important distinction in how we come to know things about the universe. There are two fundamentally different ways a telescope can study an object. The first is imaging, taking a picture, capturing the shape and the light of a thing so you can see what it looks like. The second is spectroscopy, taking the light and spreading it out to read its ingredients, learning what a thing is made of rather than what it looks like. For most of the history of astronomy, imaging is what captured the public imagination, the glorious photographs of galaxies and nebulae. But for understanding what the universe is actually made of, spectroscopy is the deeper tool, and it is the one that matters here. Because we will never have a picture of the Oort Cloud, imaging is, in a sense, off the table. We are not going to see what it looks like as a whole, ever. But spectroscopy does not need a pretty picture. Spectroscopy only needs light, even a faint thread of it, and from that thread it can pull out the chemical truth. So when a single comet falls inward and the great telescope turns toward it, we're not really trying to see the comet. We're trying to hear it, to take the light coming off it and decode the message written into that light, molecule by molecule. That is why listening is the honest word. We're not photographers of the Oort Cloud. We're something closer to its translators. And this distinction is exactly why an instrument built to study the dawn of the universe turned out to be perfect for our own backyard. The first galaxies are far too distant to photograph in any detail. They are faint smudges even to the greatest telescope. What Webb does with them is read their light, decode their chemistry and their distance and their age from the patterns in the colours. It is, at its core, a machine for reading faint light from far away and pulling meaning out of it. The Oort Cloud comets are also faint, also cold, also speaking in a language of light rather than showing themselves clearly. The skill is the same. The telescope that learned to read the first chapters of the universe turned out to already know how to read the letters falling out of our own frozen shell. It just had to be pointed in the other direction. That is the tool. That is the new kind of listening. And starting in late 2022, astronomers began turning that tool toward the messengers falling out of the cloud. And almost immediately the messengers began saying things that no one was quite prepared for. The first of them was a comet that was doing something it had no business doing, glowing and active in a part of the solar system so cold that, by every rule we thought we understood, it should have been silent and dead. That comet is where the listening really begins, and it is where we are going next. Part 4. The First Voice in the Dark. The first messenger I want to tell you about was already famous among comet scientists before Webb ever turned toward it, and it was famous for breaking a rule. The comet carries the catalogue name K2, and it was discovered in 2017 by a survey telescope in Hawaii that scans the sky for moving objects. What made it remarkable was not how bright it was or how large it was. What made it remarkable was where it was active. It had a glowing cloud of gas around it, a coma, while it was still unimaginably far from the sun. And that, by everything we thought we knew, should have been impossible. Here is why. The familiar engine that makes a comet come alive is water ice turning straight from solid to vapour, a process that needs the sun's warmth. But water ice only does that when it gets reasonably close in, somewhere around the orbit of the asteroid belt or a little beyond. Out past Saturn, out where the sunlight has thinned to a feeble trickle, water ice simply stays frozen. It does nothing. And yet this comet was already venting gas, already wrapped in a coma, when it was something like 35 times farther from the sun than the Earth is, far beyond Saturn, out in cold where water has no business doing anything at all. Astronomers had caught it being awake in a place where everything is supposed to be asleep. The explanation, it turned out, was that water was not the engine. Something more volatile was, something that boils off at temperatures far lower than water ever could. The leading suspect was carbon monoxide, a molecule so eager to turn to gas that it can drive activity in cold that would leave water utterly inert. A radio telescope detected exactly that. Carbon monoxide streaming off the comet while it was still far out in the cold. This was a body running on a different kind of fuel, a super volatile fuel, the kind of chemistry that only survives untouched in the long cold of the outer solar system. It was, in other words, behaving like exactly what it was. A traveller from the frozen reservoir still carrying the original fragile ingredients it had held onto for billions of years. So when this comet finally fell close enough for the James Webb Space Telescope to study it in detail, there was real anticipation. Here was a pristine messenger from the cloud, a body still loaded with the volatile chemistry of the early solar system, and for the first time we had an instrument capable of reading that chemistry molecule by molecule. The question was simple and enormous. What is it actually made of? You're sitting with the data as it comes down. The comet is still hundreds of millions of miles away, a faint point of light against the black, far too cold and far too distant for the eye to make anything of it. But the telescope is not using an eye. The faint light from the coma arrives at the spectrograph, and the instrument fans it out, spreading that single thread of light into a long ribbon of colour, the way a prism opens sunlight into a rainbow. At first the ribbon looks like nothing, just noise, just the faint static of a very faint thing. And then, as the signal builds, the lines begin to rise out of the noise. A bright line appears exactly where water announces itself, and water is no surprise. But then another line lifts up, in the place where carbon monoxide signs its name, and then carbon dioxide, and then, one after another, the signatures of carbon-bearing molecules, the kind of chemistry that, on a warmer world, would be the raw material of life. Each line is a molecule, each molecule is a word, and the comet, silent for billions of years in the cold, is suddenly, quietly, speaking. You're reading the chemistry of a place no one has ever been. What Webb found in that ribbon of light was not a single gas, but a whole inventory, and the inventory is the point, so let me actually name what was there. There was water, the familiar engine of ordinary comets. There was carbon monoxide, including a rare, slightly heavier version of it that scientists can tell apart, which carries its own clues about where and how the comet formed. There was carbon dioxide. And then there was a list of molecules that makes a chemist sit up, because they are the building blocks of organic chemistry. There was methane and ethane. There was methanol, a simple alcohol. There was formaldehyde. There was hydrogen cyanide, which despite its frightening name is one of the molecules scientists most want to find, because it is a stepping stone toward the chemistry that leads to the components of life. These are not ingredients that were made on Earth. They were made out there, in the cold and the dark before our planet existed, and they have been preserved in this frozen messenger ever since. I want to make sure the strangeness of that lands, because it is easy to let a list of molecules slide past. The comet was found to be hyperactive, with a remarkably large fraction of its surface venting ices, and yet the solid core driving all of it was tiny, with a radius of less than a few miles. A small object, only a few miles of ice and rock, holding within it a near-complete sample of the chemistry that was present when the solar system was assembling itself. To read that chemistry, scientists used to dream of catching a comet and bringing a piece of it home. Now, with an instrument cold enough and sensitive enough, we can read it from across the solar system, from the light alone, without ever laying a hand on it. And this is where the central thread of tonight's story really begins to pull taut. For 75 years, the Oort Cloud was a guess, a reservoir we inferred but could never describe. Now, with this one comet, we had done something genuinely new. We had not just confirmed that the cloud sends us objects. We had read one of those objects in detail and learned the actual chemistry it carried out of the dark. The cloud was no longer just a source of comets. It was beginning to become a place with a known composition, a place we could describe in the language of molecules. The guess was starting, finally, to become a place. I want to linger on the organic molecules for a moment, because they are easy to skip past and they are, in many ways, the most important thing in the whole inventory. When scientists talk about organic chemistry, they do not mean life. They mean the chemistry of carbon, the family of molecules built around carbon atoms that, under the right conditions, can become the components of living things. The molecules Webb read in that comet, the methanol and the formaldehyde and especially the hydrogen cyanide, are not life and not signs of life, but they are the rungs on the ladder that leads toward life. Hydrogen cyanide in particular is a molecule that researchers study intensely because pathways exist that lead from it toward the building blocks of the genetic material that all life on Earth uses. To find it preserved in a comet falling from the Oort Cloud is to find one of the earliest rungs of that ladder, intact from before the Earth existed. This is why these frozen messengers matter so much beyond the question of where comets come from. There is a long-standing idea that some of the water and some of the carbon chemistry that made life on Earth possible may have been delivered, at least in part, by comets and similar bodies early in our planet's history. Whether or not that turns out to be the full story, the comets are carrying the same kind of chemistry that was present when the planets, and eventually we, were assembled. Reading that chemistry in a body that has been sealed in the cold since the beginning is as close as we may ever come to looking directly at the raw ingredients of our own origin, untouched and unaltered, exactly as they were. And the fact that we can read all of this remotely, without ever touching the object, is itself a kind of quiet miracle that I do not want to pass over. There were serious proposals for decades to do this the hard way, to chase down a comet with a spacecraft, fly alongside it, even capture a piece of it and bring it home, because that seemed like the only way to truly know its chemistry. Those missions are difficult, enormously expensive, and rare. What the new generation of instruments has done is change the rules. We can now read the detailed molecular makeup of a body more than 1 billion miles away, from the light alone, in a single set of observations. The comet does not have to come to us, and we do not have to go to it. The light it gives off is enough. We have learned to hold a frozen messenger up to a prism and read its entire chemical biography in the colours that come through. There is a finer clue buried in that inventory that I find genuinely beautiful, and it is the rare, slightly heavier form of carbon monoxide that the telescope detected alongside the ordinary kind. Some atoms come in slightly different weights, called isotopes, depending on how many particles sit in their core, and the exact ratio of the lighter to the heavier versions in a comet is a kind of thermometer for the past. It records something about the temperature and the conditions in which the ice first formed, billions of years ago. By reading not just which molecules are present, but the precise mix of their isotopes, scientists can begin to ask where in the young solar system a particular comet was assembled, and how cold it was when its ices froze. The comet is not just telling us what it is made of, it is telling us, faintly, where and when it was made. That is the kind of detail that turns a single observation into a piece of history. A few years ago, the best we could hope for from a distant comet was to know it was there and roughly how bright it was. Now we can read its molecules, weigh its isotopes, and begin to reconstruct the conditions of its birth at the dawn of the solar system, all from a thread of light gathered across more than 1 billion miles. Each comet, read this carefully, becomes less like a rock and more like a document, written in a chemistry that has not been edited since before the Earth existed. And the more of these documents we gather, the more we can begin to read not just the individual pages, but the shape of the library they came from. But one comet is one comet. One messenger, however eloquent, is still just a single voice. To know whether what this comet was telling us was true of the whole cloud, or whether it was a strange exception, you would need to listen to more of them. You would need to compare. And as Webb and other instruments turned toward more of these falling visitors, the picture did not get simpler. It got stranger. Because the next messenger was not a small tidy core a few miles across. The next messenger was a mountain, a frozen object so large that, by the rules we thought governed the outer solar system, it should not exist at all. Part 5. The mountain that should not exist. The second messenger has one of those names that sounds like a law firm, and behind the name is a story about how discovery actually happens now, which is to say, often by accident, hidden inside data that was gathered for something else entirely. The comet is called Bernardinelli-Bernstein, after the two researchers who first recognised it, and it is the largest comet anyone has ever found falling in from the Oort Cloud. To call it a comet almost undersells it. It is a frozen mountain on a 3 million year orbit, and the fact that it exists at all has forced astronomers to reconsider what is really out there in the dark. It was not found by someone searching for comets. It was found by Pedro Bernardinelli, who at the time was a graduate student, working with Gary Bernstein at the University of Pennsylvania. The two of them were sifting through images from a project called the Dark Energy Survey, an enormous effort that had photographed huge stretches of the southern sky over 6 years, not to find comets at all, but to study how the universe is expanding. Buried in those hundreds of thousands of images was a faint object that nobody had flagged before. It was visible only because the survey was so sensitive and so wide that it had accidentally swept up a comet most telescopes would have missed entirely. And as the team traced its slow motion backward through years of archived photographs, they realised it had been quietly falling toward us the whole time, getting nearer year by year, unnoticed. Then they ran the numbers on its size, and the numbers came back wrong. Not wrong as in mistaken, wrong as in impossible. The solid core of Bernardinelli-Bernstein, the frozen core of the comet, is roughly 85 miles across. I want to give you a moment with that figure because it is so far outside what a comet is supposed to be. The famous comet Hale-Bopp, the one that hung in the sky and amazed people in 1997 and was considered enormous at the time, had a core somewhere around half this size. The even more famous Halley's Comet has a core only about 9 miles across. Bernardinelli-Bernstein is roughly 10 times the size of Halley. It is larger than most of the objects in the entire asteroid belt. If you set one end of it down in Lower Manhattan, the other end would reach Philadelphia. This is not a dirty snowball. This is a frozen country, falling toward the sun. Now hold that size in your mind and bring back something I told you a moment ago. The standard story of how the Oort Cloud formed says that these objects were flung out there billions of years ago by the gravity of the giant planets, Jupiter and Saturn and the others, slingshotting leftover debris from the inner solar system out into the cold. And the models of that violent process predict that the objects scattered outward should mostly be small. Chunks of ice. Boulders mostly. The math does not comfortably allow for mountain-sized comets to be common out there. A single 85-mile object is hard enough to explain, and here is the part that should make the back of your neck prickle. If an object this large exists out there, it is almost certainly not alone. We did not happen to find the one freak giant in a cloud of pebbles. We found one of the large ones because the large ones are the only ones we could possibly detect at that distance. For every mountain we can see falling toward us, there are in all likelihood a great many more we cannot. The cloud is not just sending us small messengers, it is hiding a population of giants we are only beginning to suspect. There is one more thing about this frozen mountain that matters for our story, and it is the part where I have to be precise, because this is exactly where the popular telling of this tale goes astray. As Bernardinelli-Bernstein fell inward, while it was still extraordinarily far out, more than 16 times the Earth-Sun distance from the Sun, well beyond the orbit of Saturn, it was already active. It was already venting gas in cold so severe that water ice could not possibly be the cause. And the instrument that caught it doing this was not the James Webb Space Telescope. It was a different tool, a powerful array of radio dishes high in the mountains of Chile called ALMA. ALMA detected carbon monoxide streaming off this comet at that incredible distance, the most distant detection of that kind of activity in any comet ever recorded at those wavelengths. The ice was bleeding slowly and quietly in the cold beyond Saturn, venting gases that had been locked away for over 4 billion years. I point this out not to be pedantic, but because the truth is actually better than the myth. The popular version says one telescope did everything. The reality is that we now have a whole set of instruments working together, each contributing a different sense. A radio array in Chile can detect the cold outgassing of a comet, at distances that would have been unthinkable a generation ago. A great infrared telescope in space can read the detailed molecular fingerprint of another comet's coma. Ground-based survey telescopes can find these objects in the first place, sometimes by accident, in data gathered for entirely different reasons. The reason the Oort Cloud is finally becoming a place is not one heroic machine. It is a chorus of them, and Bernardinelli Bernstein has been heard by more than one voice in that chorus. But step back from the instruments for a moment and just sit with the object itself, because I think it deserves it. Out beyond Saturn, in cold only a few degrees above the lowest temperature the universe permits, an 85-mile mountain of 4-billion-year-old ice is drifting inward, on an orbit so long that the last time it came this way, if it ever did, there were no human beings to see it, and the next time it returns, in roughly 3 million years, there may be none either. And it is not silent. It is exhaling, very faintly, the frozen breath it has held since before the Earth had finished forming. We caught it in the act. We caught a frozen country breathing in the dark. It is worth pausing on the human side of this too, because it is easy to forget there are people in this story. Somewhere, a graduate student was clicking through archived images of the southern sky, images taken to measure the expansion of the universe, and noticed a faint smudge that had been sitting in the data, unremarked, the whole time. And that smudge turned out to be the largest comet ever found, a frozen whirl the size of a small American state that had been falling toward us in plain sight, recorded but unseen, for years. The cloud had sent us its largest known messenger, and it very nearly slipped past us entirely. How many others have slipped past? How many mountains have fallen toward the sun and back out again while we were looking the other way? The honest answer is that we do not know, and that not knowing is its own kind of vertigo. The accidental nature of this discovery is worth sitting with, because it tells you something humbling about how much is still out there waiting. Bernardinelli Bernstein was not found by anyone looking for it. It was sitting in years of archived images, gathered for a completely different purpose, recorded but unrecognized, the largest comet ever known, hiding in plain sight in data that human beings had already collected. It took a careful search through that old data, by a graduate student willing to look, to notice that one of the faint moving smudges was something extraordinary, which raises an unsettling question. If the largest comet we have ever found was sitting unnoticed in data we already had, how many other giants have passed through our records, or our skies, completely unremarked? How much have we simply failed to see, not because it was hidden, but because we were not looking carefully enough, or did not yet have the tools to recognize what we were seeing? The orbit of this frozen mountain is its own kind of poetry, and it reinforces everything we said about the silence and the patience of the cloud. Bernardinelli Bernstein is on a path that takes it roughly 3 million years to complete. 3 million years. The last time it came this way, if it ever did before, our ancestors were not yet anything we would recognize as human. By the time it returns to the cold and falls inward again, 3 million years from now, there is no telling what, if anything, will be here to notice. We're catching it during the single brief window of its entire multi-million-year orbit, when it passes close enough for us to study. We happen to be alive and watching, and equipped with the right instruments, during the one short act of a play that lasts longer than the human story. That is not something to take for granted. It is a kind of cosmic luck, and it deepens the central puzzle. Every model of how the cloud formed predicted that the objects flung out there should mostly be small. The presence of even one mountain of this size means the models are missing something, and the presence of a likely population of such mountains means they are missing something large. The cloud is not behaving like the tidy, well-understood reservoir of theory. It is behaving like a place with surprises in it, a place that holds more and larger and stranger things than we expected, a place that, the more carefully we listen, keeps telling us we underestimated it. So now we have 2 messengers and 2 lessons. The first comet told us the cloud is full of pristine, fragile chemistry, the original ingredients of the solar system preserved in the cold. The second told us the cloud holds objects far larger and more numerous than our models expected, a hidden population of giants. Put those two lessons together and the old picture, the picture of a thin scattering of dirty snowballs, starts to fall apart. Something richer and stranger is out there. And the best way I know to make you feel it, before we talk about what it means, is to take you there. To put your feet for a few minutes on the surface of one of these distant worlds and let you stand in the place that for 75 years was nothing but a line in an equation. Part 6. Standing on the edge of everything. Let yourself drift for a while now, because I want to take you somewhere, and the only way to really go there is slowly. Imagine you're standing on the surface of one of these distant bodies, far out in the Oort Cloud. Not a giant like the frozen mountain we just talked about, but an ordinary one, the common kind, only a few miles across. You're standing on a small world at the outer edge of the sun's kingdom, and I want you to take your time and look around, because almost no one in the history of thought has stood here, even in imagination, with as much real knowledge of what it would be like as we have right now. The first thing you would notice is your own weight, or rather, the near total absence of it. The object beneath your feet is so small that its gravity barely registers. You do not so much stand on it as rest against it. If you bent your knees and pushed off gently, the way you might step off a curb, you would rise and keep rising, drifting upward for minutes at a time, slowly turning, before the faint pull of the little world coaxed you back down. There is no danger in it, no sudden fall. Everything here happens slowly. A pebble you nudge with your boot would float away in a long, lazy arc. A breath, if you could breathe here, would push you backward. You're less a person walking on a world than a person sharing an orbit with one, the two of you falling together around a distant sun. The ground beneath you is not rock. It is ice, but not the ice you know. Out here, where the temperature sits only a few degrees above absolute zero, water ice is not soft or slippery. It is harder than steel, compacted and hardened over billions of years of cold and vacuum into something more like stone than like anything you would call frozen water. If you struck it, it would ring. Mixed into that ice are the darker materials, the carbon-bearing compounds, the original chemistry of the early solar system, the same molecules we read in the light of the comets, here in their solid resting state, undisturbed since before the Earth was whole. You're standing on a sample of the beginning of things, perfectly preserved because nothing out here has ever happened to disturb it. No weather, no warmth, no light to speak of, just the long, patient cold, holding everything exactly as it was. Look up now. The sky above you is black, and it is a black far darker than any night you have ever seen on Earth. There is no air here to scatter light, no thin blue veil, no glow on the horizon, because there is no horizon and no atmosphere. The darkness comes right down to the ice at your feet, and scattered across that perfect black are the stars, and they are like nothing you have seen from any backyard or any mountain top. They do not twinkle, because twinkling is something air does to starlight, and there is no air. They are simply there, fixed, sharp, unwavering, like pinpricks cut through a curtain of the deepest black imaginable. More of them than you have ever seen at once, and every one of them perfectly still. Somewhere among those stars is the sun, and this is the part that I think changes something in a person, even just to imagine it. From here, the sun is not the source of warmth and life that fills the sky of Earth. From here, the sun is just a star, a bright one, brighter than its neighbours, but a star nonetheless, a single point of light you would have to actually look for. You could hold up a hand and hide it behind a fingertip. It gives you no warmth you could feel. It casts almost no light on the ice around you. The thing that anchors your entire home, the star that everything you have ever known orbits around, is from out here just one more bright dot among the others, easy to lose if you glanced away. You're still, technically, inside the sun's family. You're still bound to it, still falling in its enormous gentle gravity. But you would never know it to look. You feel, standing here, like you're already among the stars because in every way that your senses could tell you, you are. And then there is the silence. I want you to really sit in this, because it is unlike any quiet you have ever experienced. On Earth, even in the most remote and silent place you can find, there is always something. The faint movement of air, the sound of your own blood, some distant, almost inaudible hum of a living, moving world. Out here there is none of it. There is no air to carry sound, so there is no sound. There is no wind, because there is nothing to be wind. There is no motion anywhere around you, except the impossibly slow turning of the stars as your little world creeps along its orbit. The silence is not the absence of noise. It is something more complete than that. It is the silence of a place where, for billions of years, almost nothing has happened at all. And the orbit. The orbit is the thing I most want you to carry away from this place. The little world you're standing on is moving, falling around the distant sun, but so slowly on a path so enormous that a single trip around takes longer than you can easily hold in your head. Out in the far reaches of the cloud, one orbit, one single lap around the sun can take millions of years. Let me try to make that real. If this little world began one lap around the sun at the moment the first simple life appeared on Earth, billions of years ago, it might only now be completing it. A single year for this world is longer than the entire history of life on our planet. The last time it was at this exact point in its path, there was no human civilization, no agriculture, no language, no fire. The next time it returns, there may be none of those things either. It does not know about us. It has never known about us. It simply falls in its long, slow, silent circle, indifferent and patient and old. This is the place. Not a graveyard, not a void, but this. A small, dark, frozen world, holding the original chemistry of the solar system in ice harder than stone, drifting through a silence older than life, under a sky where the sun is just another star, on an orbit longer than memory. And it is not alone. In every direction you could look, scattered through a volume so enormous that you would likely never see your nearest neighbour with your own eyes, there are trillions of others. Trillions of small, dark, frozen worlds, each one resting in the same silence, each one falling on the same kind of impossibly slow orbit, each one a sealed container of the distant past. You're standing in the middle of the largest structure in our solar system, and it feels, from where you stand, like the loneliest and emptiest place imaginable. That is the paradox of the Oort Cloud, and it is one we're going to have to make peace with. It is empty in the sense that there is nothing nearby. It is full in the sense that there is something almost everywhere. Before you leave that little world entirely, let your eyes adjust to the dark a while longer, because there is one more thing to feel out here, and it is the most disorienting of all. You're not alone, and yet you're more alone than any human being has ever been. Scattered through the immense space around you, in every direction, are the others, trillions of frozen worlds just like the one beneath your feet. You're standing in the middle of the most populated region of the entire solar system, and you cannot see a single one of your neighbours. The distances between the bodies of the cloud are so enormous, often millions of miles, that even surrounded by trillions of companions, the sky holds no sign of them. There is no crowded field of nearby worlds, no neighbouring ice catching the faint light. There is only the black and the unmoving stars and the single distant point of the sun, and you. That is the truth of this place that no diagram ever captures. In pictures, the Oort Cloud is always drawn as a dense glittering shell, a thick fog of icy bodies packed close together. The reality is the opposite. If you took every grain of sand on every beach on Earth and scattered it through a sphere reaching most of the way to the next star, that is roughly how thinly the cloud is populated. It is less a shell than a suggestion of a shell, a statistical haze of objects so spread out that, from any one of them, the cloud itself is invisible. You would never know, standing here, that you were inside the largest structure belonging to our sun. You would feel only the emptiness, and the cold, and the silence, and the strange, slow turning of an orbit older than memory. And maybe that is the right note to drift on, here in the middle of our journey. The Oort Cloud is the part of our solar system that most resembles the gap between the stars itself, the long, cold, nearly empty dark, and yet it is unmistakably ours, bound to our sun, made in part of our own beginning. It is the threshold between home and the wider galaxy, a place that is both, the last outpost of the familiar and the first taste of the truly distant. To stand here, even in imagination, is to stand with one foot in our solar system and one foot in interstellar space, and to know, as we now do, that this threshold is not empty but full, is to feel the comfortable boundaries of home quietly dissolve. Stay in the slowness a moment longer, because time itself feels different out here, and that difference is part of what the place is. Even light, the fastest thing there is, struggles with these distances. Sunlight that left the sun takes only minutes to reach the Earth, but out at the inner edge of the cloud, that same light has been travelling for nearly 2 weeks before it arrives, and out at the far edge more than a year. You're so far from home that the sun you see is old news, a message sent long before you turn to look. Everything here is patient. Everything here is slow. The light is slow to arrive, the orbit is slow to turn, and the cold is so complete that change itself has nearly stopped. If there is a place in our solar system where time comes closest to standing still, it is here, in the long, frozen quiet of the outer cloud, where a single year can be longer than the whole human story. Come back now, gently from that surface. Come back to your room, to your bed, to the warmth and the air and the quiet sounds of a living world. But carry the place with you, because everything we say from here will be richer for having stood there. We have read 2 of the messengers, and we have stood in the country they come from. Now it is time to ask the question that all of this has been building toward. What is the Oort Cloud actually telling us when we listen to enough of its voices at once? Because the comets, it turns out, do not all say the same thing, and the differences between them are where this story stops being about ice and starts being about something far harder to hold. Part 7. The Archive, Not the Graveyard. When you listen to one comet, you learn about one comet. When you listen to many, you start to learn about the place they come from, and you start to notice the differences between them. And the differences are where the Oort Cloud stops being a simple idea and starts becoming something with structure, with regions, with a history you can almost read. This is the shift I find most remarkable in everything the new instruments have given us. We did not just confirm the cloud, we began to discover that it is not uniform, that it is layered and varied, and that it holds information no other place in the solar system can give us. Start with a comparison that sounds technical, but matters enormously. There are 2 main reservoirs of icy bodies in the outer solar system. There is the closer one, the ring beyond Neptune that we call the Kuiper Belt, the source of the short-period comets that come back every few decades. And there is the far one, the great surrounding shell, the Oort Cloud, the source of the long-period visitors. For a long time, you might have assumed these 2 were basically the same stuff, just at different distances. But when scientists began carefully comparing the chemistry of comets from the 2 reservoirs, they found that the fingerprints do not match. The Oort Cloud comets carry a different signature. They tend to be more loaded with carbon-bearing molecules, more abundant in the most volatile ices, the ones that boil away at the lowest temperatures. They read, in some hard-to-define sense, as older and more pristine, as though they preserve an earlier and more fragile stage of the solar system's birth, a stage that the closer reservoir has partly lost. Think about what that means. Even though all of these objects, near and far, formed during the same chaotic era around the young sun, they are not telling the same story. The Oort Cloud is not just a more distant version of the Kuiper Belt. It is a different archive, holding a different chapter. and that single fact transforms how we have to think about it. We are no longer studying a generic frozen graveyard, a junk drawer of identical leftovers. We are studying a structured, layered, chemically varied region that has held onto a record the inner solar system long ago erased. And here is why that erasure matters so much, and why these distant, frozen bodies are worth all this trouble. Everywhere closer to the sun has been changed. The Earth has been melted and reformed and weathered and reworked, its original chemistry buried beyond recovery under billions of years of geology and oceans and life. Mars has been baked by radiation and scoured by dust, its early record battered and altered. Even the moon is a cratered, blasted shell, hammered by impacts for billions of years. If you want to know what the chemistry of the very early solar system was actually like, you cannot dig for it on any of these worlds, because on all of them, the original ingredients have been cooked and scrambled past reading. But out in the Oort Cloud, nothing has happened. The bodies out there have been sitting in the cold, untouched by heat and radiation and impact, doing absolutely nothing for 4.5 billion years. They are not construction debris. They are time capsules, sealed at the moment of the solar system's formation and never opened. This is the idea that astrobiologists like Caleb Scharf have been arguing for years, that we badly underestimate the outer solar system, that we treat it as empty and dead when in fact it is the single best preserved record of our origins that exists anywhere we can reach. You do not learn what the early solar system was made of by studying the worlds that have been changed beyond recognition. You learn it by reading the things that have been doing nothing in the long cold since the beginning. And that is exactly what the falling comets let us do. Each one is a sealed sample of the original chemistry, delivered to us, one at a time across thousands of years. We just needed instruments sensitive enough to break the seal with light and read what is inside. But the comets are doing more than confirming that the cloud is a pristine archive. They are revealing that the archive has internal structure, and this is where the work of scientists like Karen Meach at the University of Hawaii becomes so important. The approach is no longer to study one spectacular comet in isolation. It is to gather the readings from many long-period comets and lay them side by side, building a comparative picture, asking how they differ and what those differences mean. And when you do that, the comets refuse to fall into a single tidy category. Some of them appear to be genuinely ancient members of the cloud, bodies that have never once approached the sun, falling in for the very first time after billions of years of perfect cold. Others are what scientists call dynamically new, recently disturbed and freshly falling, and their compositions vary in ways that hint the cloud itself is not the same everywhere, that there may be regions more loaded with carbon, regions more loaded with water, layers and zones within that enormous shell. There may even be, and this is the possibility that begins to open a door we will walk all the way through shortly, regions of the cloud that contain material that did not form around our sun at all, material that came from elsewhere, captured long ago, mixed into our own frozen reservoir. But I am getting ahead of the story. For now, hold on to the structure, because it is a genuine discovery and it changes the character of the place. The Oort Cloud is not a uniform fog of identical snowballs. It is a layered, varied, structured region, with an inner part and an outer part, with chemical zones, with members of different ages and different histories. It has, in a word that I do not use lightly, a biography. A place with a biography is not a guess anymore. A place with a biography is a place. And I want you to feel how far we have come in just a few years, on a question that stood unanswered for 3/4 of a century. Jan Oort could tell us the cloud existed. He could tell us roughly how big it was and where the comets came from. But he could not tell us what it was made of, and he could not tell us whether one part of it differed from another, and he could not tell us how old its members were or how varied. Those questions were simply beyond reach. Now, comet by comet, fingerprint by fingerprint, we are beginning to answer them. We are sketching the first chemical portrait of a place no human will ever visit, and the portrait is more detailed and more surprising than anyone expected. The graveyard turned out to be a library, and we have only just learned how to read the spines of the books. The idea that some of these bodies have never once approached the sun is worth pausing on, because it is genuinely strange to consider. There are comets falling toward us now that are, in a real sense, brand new to sunlight. For 4.5 billion years they have hung in the outer cloud, in cold so severe that nothing about them has changed, and only now, for the first time in the entire history of the solar system, are they falling close enough for the sun's warmth to touch them. When such a comet brightens, the gases lifting off it are being released for the very first time since the object formed. We are witnessing the literal first breath of a body older than the Earth, and because nothing has ever disturbed it, what we read in that first breath is the purest possible sample of the original chemistry, undisturbed by any previous trip past the sun. Compare that to the comets we have known longest, the ones that return again and again on shorter orbits. Every time one of those passes the sun, it loses a little more of its volatile chemistry, its surface baked and altered, its most fragile ice is driven off. After enough passes, what remains is a changed and depleted thing, no longer a clean record of its origin. The long-period comets from the far cloud are different precisely because they are pristine. They have not been worn down by repeated encounters with warmth. They are first editions, where the closer comets are well-thumbed reprints. And the new instruments let us tell the difference. Let us read which comets are ancient and untouched, and which are altered, and from that, begin to sort out the structure and the history of the cloud they came from. This is the work that turns a collection of individual comets into a picture of a place. No single comet, however remarkable, can tell you the shape of the whole cloud. But lay enough of them side by side, sort them by age and by chemistry, and by where in the cloud they seem to have come from, and slowly a portrait emerges. Regions that seem more loaded with carbon, regions that seem more loaded with water, an inner layer and an outer layer that may differ in subtle ways. The beginnings of a sense that the cloud is not one uniform thing, but a structured archive with chapters and sections. We are, in the most literal sense, reading the cloud the way you might reconstruct a lost library from the scattered pages that occasionally drift out of it, one page at a time, slowly learning the shape of the whole. There is one more thread in this archive that I've been holding back, because it deserves its own place in the story, and it is the strangest and most far-reaching of all. Among all these frozen messengers, all these sealed time capsules of our own beginning, there is a growing suspicion that some of them are not ours, that mixed into the shell around our sun is material born around other stars, carried across the immense dark between, and quietly stored in our own backyard. To understand how that could possibly be true, we have to talk about the rare and extraordinary objects that have come, in recent years, not from our cloud, but from somewhere else entirely. Part 8. The Travellers from Other Suns. Until very recently, everything that fell toward the sun belonged to the sun. Every comet, every asteroid, every wandering chunk of ice and rock was a member of our own family, born here, bound here, falling along an orbit that would eventually bring it back. The idea that something could fall through our solar system from outside, from another star entirely, was a theoretical possibility that nobody had ever caught in the act. Then, in the space of just a few years, we caught it 3 times, and the 3rd time we read its chemistry, and what we found ties this whole story together in a way that I still find difficult to fully absorb. The first one arrived in 2017. A survey telescope in Hawaii picked up a small, fast-moving object on a path that made no sense for anything belonging to our solar system. It was not on an orbit at all, not really. It was on a trajectory, falling in from the direction of the constellation Lyra, whipping around the sun, and leaving again, never to return. It had come from another star. We named it Oumuamua, a Hawaiian word that means, roughly, a scout or a messenger from far away, one reaching out. It was strange in almost every way. It appeared to be oddly elongated, tumbling and reddish, and it showed a faint, unexplained push as it left, a slight acceleration that no one could fully account for. It was here and gone in a matter of weeks, and it left far more questions than answers. But it proved beyond any doubt that objects from other star systems pass through ours. The second one arrived in 2019, found by an amateur astronomer named Gennady Borisov. This one was less ambiguous. It was unmistakably a comet, with a proper coma and tail, but again on a trajectory that showed it had come from interstellar space, falling through our system from somewhere else and heading back out forever. And because it was an ordinary-looking comet, we could study its chemistry, and we found that it carried the signature of another planetary system, chemistry that formed around a different star, delivered briefly into range of our telescopes before it left for good. 2 interstellar visitors in 2 years, after a lifetime of catching none. It was becoming clear that these things are not freak events. They are passing through all the time. We simply could not see them until our instruments improved. And then came the third, and the third is the one that matters most for our story, because by the time it arrived, the James Webb Space Telescope was watching. This object, the third confirmed interstellar visitor, fell in from the dark like the others, and when Webb turned its mirror toward it and read the gas surrounding it, the result was arresting. The cloud of gas around this traveller was not dominated by water, the way most comets in our own system are. It was dominated by carbon dioxide. The ratio of carbon dioxide to water in its coma was among the very highest ever measured in any comet, anywhere. A lopsided chemistry that stood far outside the normal range of the comets born around our own sun. This was not our chemistry. This was the chemistry of somewhere else, formed in the cold around a different star, under conditions we can only guess at, and carried across hundreds of light years to arrive, briefly, where we could read it. Let me make sure the weight of that lands, because it is easy to let it slide past as just another measurement. For the first time, we pointed our finest instrument at a piece of another solar system, an actual physical object made of the ices and gases of a foreign star, and we read what it was made of. Not light from a distant world, not the atmosphere of a planet we can never reach, but a tangible body, right here, passing through, carrying the recipe of its birthplace written into its ice. The chemistry was foreign. The proportions were wrong for anything from home. We were, in the most literal possible sense, holding a sample of another planetary system up to the light and reading it. Now, I have to be careful and precise again, because this is the kind of fact that gets distorted in the retelling, and the truth matters. This carbon dioxide-heavy traveller was not a member of the Oort Cloud. It was an interstellar object passing through, born around another star. The Oort Cloud is our own, made of our own sun's leftovers. So why am I telling you about a foreign visitor in the middle of a story about our own frozen shell? Because the existence of these travellers, and our new ability to read them, raises a question that turns the entire story of the Oort Cloud on its head. If objects from other stars pass through our solar system regularly, as we now know they do, then here is the question that follows, and it is the question that some researchers have started to take very seriously. How many of them do not just pass through? How many of them get caught? Think about it carefully. An object falls in from another star, crossing the immense dark between the suns. Most of them, like the 3 we have seen, are moving too fast, on trajectories too steep, and they whip around our sun and leave. But not all of them would be moving the same way. Some would be slower, some would come in at just the right angle, at just the right speed, to be captured, to have their path bent by the sun's gravity until, instead of leaving, they settled into a long, distant orbit and stayed. And where would a captured interstellar object end up? Not in the inner solar system, where the planets would quickly disturb it. It would end up far out, in the one place that gently collects and holds slow, distant objects for billions of years. It would end up in the Oort Cloud, so the visitors passing through are not just a curiosity running alongside the main story. They are a clue about the main story. They are direct physical proof that material from other stars crosses our system, and that gives real weight to a possibility that would otherwise sound like pure speculation. The possibility that our own Oort Cloud, the shell of frozen bodies surrounding our Sun, is not entirely ours. That somewhere in that enormous, dark, silent reservoir, mixed in among the 4.5 billion-year-old time capsules of our own beginning, are bodies that formed around other stars captured long ago and stored ever since in the cold of our own backyard. Consider how quickly our sense of these visitors has changed. For the entire history of astronomy up to 2017, not a single object from beyond our solar system had ever been caught passing through it. The idea was sound in theory, but we had never seen it happen. Then, in the span of just a few years, we found 3. That tells us something important. It is not that interstellar objects suddenly started arriving. They have almost certainly been passing through the whole time, for billions of years, in numbers we're only beginning to estimate. What changed is us. Our survey telescopes finally became good enough to catch them in the act. And if we found 3 in a few years once we could see well enough, then the true rate of these visits must be far higher than 3 in a few years. They're passing through constantly, a steady traffic of foreign material crossing our system, almost all of it unseen. Now follow that thought to its conclusion, because this is where it becomes remarkable. If foreign objects are constantly crossing our solar system, then over the 4.5 billion years of the Sun's life, an enormous number of them must have passed through. The overwhelming majority would have come and gone too fast to be caught. But gravity is patient, and probability is relentless. Out of the countless interstellar bodies that have crossed our system over billions of years, some fraction, arriving at the right speed and the right angle, would have been slowed and captured by the combined pull of the Sun and the planets, bent out of their escape and into a long bound orbit. And captured objects, as we have said, tend to settle into the one place that holds distant orbits for the long term. They tend to settle into the Oort Cloud. So the visitors we can see, the rare ones we catch streaking through, are only the visible edge of a much larger, invisible story. For every interstellar object we observe passing through, there may be many that pass through unseen, and some small share of all of them, accumulated over the entire history of the solar system, that never left. The reading of that carbon dioxide heavy traveller by the Great Telescope was not just the study of one foreign comet. It was a proof of concept, a demonstration that we can now identify and read the chemistry of material from other stars when it comes within reach. And that capability is exactly what we would need to someday catch one of these captured immigrants in the act of falling from our own cloud and recognize it for what it is. The way we even know these objects are foreign is worth a moment, because it is wonderfully simple. Everything bound to our Sun moves at a certain range of speeds and along certain kinds of closed paths, looping orbits that return. An object falling in from another star carries the speed of its long journey between the suns, and it arrives moving too fast to be held on an open path that bends around the Sun once and leaves forever. You can tell, just from the geometry and the speed, that it was never ours, that it came from outside and is only passing through. That is why astronomers now mark them with a simple, almost ceremonial naming system, a number followed by the letter that stands for interstellar, the first, the second, the third, a quiet new catalogue of the things that come from beyond. Each one is a confirmed traveller from another star, and the list, until recently empty for all of history, is now growing. That is the door this whole part of the story has been walking toward, and now we're going to step through it. Because if it is true, even a little bit true, it changes what the Oort Cloud is. It would mean the cloud is not only our solar system's archive, it would mean it is, in part, a sample of the galaxy itself, quietly collected over billions of years and held in a place we have only just learned to read. And it would mean that the sentence on the thumbnail that brought you here is not a metaphor at all. It would mean it is simply, literally true. Part 9. We are not alone in our own backyard. Our Sun was not born alone. This is one of those facts that sounds almost poetic, but is, as far as we can tell, simply true. Stars do not form one at a time in isolation. They form in groups, in great clouds of gas and dust that collapse together and give birth to hundreds or thousands of stars at once. All of them siblings, all of them crowded close together in a stellar nursery. Our Sun was one of those siblings, 4.5 billion years ago, packed into a cluster with many others, all of them forming their own planets, their own debris, their own frozen reservoirs at the same time. And then, slowly, over hundreds of millions of years, the cluster drifted apart and the Sun's siblings scattered across the galaxy, until now they are lost among the stars, unrecognizable, impossible to find. But here is the thing about being born in a crowd. When the Sun was young and its neighbours were close, the outer reaches of all those young planetary systems would have brushed against one another. The faint, loosely held outer comets of one star would have drifted within reach of another. And in that crowded early time, there would have been a great deal of trading. Comets flung out from one young star could have been caught by a neighbour. The outer clouds of sibling stars could have overlapped and mingled. Some models suggest that a meaningful fraction of the bodies in our own Oort Cloud may not have formed around our Sun at all, but were captured from our stellar siblings during that crowded infancy, and have been sitting in our cloud ever since, long after the siblings themselves wandered away and were lost. And then, layered on top of that, there is the slower, longer process we just talked about. For 4.5 billion years since, our Sun has been drifting through the galaxy, and interstellar objects have been falling through our system the whole time, the way we have now directly seen them do. Some fraction of those, the slower ones, the ones arriving at just the right angle, would have been captured and stored in the cloud as well. So there are two ways that foreign material could be sitting in our backyard. There is the early trading among siblings, and there is the slow, ongoing capture from the galaxy at large. And our recent observations of objects from other stars passing through have made both of these possibilities far harder to dismiss. We used to be able to wave them away as untestable speculation. We cannot anymore, because we have watched the raw material of the process fall past us, 3 times in a decade. I want to slow down now and let this settle, because we have arrived at the centre of what the title promised you, and it deserves to land with its full weight rather than rush past. For your entire life, and for the entire life of everyone who has ever lived, the space around our Sun has been imagined as ours, our solar system, our planets, our Sun, our little corner of the galaxy, separate and self-contained, with the cold dark between the stars as a clean and empty boundary. What the new science is suggesting is that this boundary was never clean, and the corner was never entirely ours. The shell of frozen worlds that surrounds us, the largest structure in our solar system, may be a mixture. Partly our own beginning, partly the beginnings of stars we will never identify. All of it stirred together and held in the cold, a shared inheritance from a galaxy full of other suns. The void we used to call empty is not empty, and it may not even be entirely ours. We're sitting inside a structure that is, in part, made of elsewhere, and we never knew it was there at all. That is the terror in the title, and I want to be clear about what kind of terror it is, because it is not the terror of danger. Nothing out there is coming for us. The Oort Cloud is not a threat. The fear, if you want to call it that, is the fear of scale and of belonging, and of how small and how recent our knowledge is. It is the vertigo of discovering that you have been standing your whole life inside a room you did not know existed, surrounded by objects you cannot see, some of which came from places you will never find, in a structure so large and so old that your entire civilization is a single blink within a single one of its orbits. It is the feeling of the ground, of the familiar tilting underneath you, and the comfortable, empty backyard turning out to be a galactic-scale archive that you happen to live in the middle of. Come with me one more time, out into the dark, and ride a single one of these travellers home. It has hung in the outer cloud for longer than there has been complex life on Earth, motionless, frozen, one more point of dark ice among trillions. Its ices were not made here. They formed in the cold around another star, in a stellar nursery that scattered and vanished billions of years ago. And somehow, in the crowded early days, our young sun caught this small frozen thing and kept it. For 4.5 billion years it has waited, asleep, indistinguishable from our own. And now, far out beyond everything, the faint gravity of a passing star reaches in and gives it the gentlest possible nudge. Feel the long fall begin. For millions of years it drifts inward, gathering the slowest imaginable speed, falling toward a brightening point of light that its makers never knew. And at last it rounds a star that is not the star it was born under, warms in a light that is not its first light, and unfurls a tale of foreign chemistry across our sky. By the time it reaches us, the star that made it may no longer exist. The comet is the only thing left of an encounter that happened in another age of the galaxy, and we are the first eyes ever to read it. When a comet falls toward our sun, then, there is a chance, however small, that we are not looking at our own material at all. There is a chance we are looking at a piece of another world, born in the gas clouds around another star, drifting across hundreds of light years before our sun caught it, and only now falling close enough to read. This is not poetry. This is a real, physical possibility that working scientists take seriously, and our new ability to read the chemistry of these objects is exactly the tool that may, someday soon, let us prove it for a specific comet, to point at one falling visitor and say, with confidence, that one is not from here. We have not done it yet, but for the first time it is no longer unthinkable. For the first time it is a question we know how to ask. Let yourself feel the full strangeness of the timeline here, because it stretches the mind in a way that is worth the effort. The sun's siblings, the stars it was born alongside, are not gone in the sense of destroyed. They are still out there, scattered across the galaxy, ordinary stars going about their lives, some of them perhaps with planets and life of their own. We simply cannot tell which ones they are anymore. The cluster dissolved so long ago, and the stars have drifted so far, that our family is lost in the crowd of the galaxy, unrecognizable. And yet, if the capture idea is right, we may be holding pieces of those lost siblings in our own cloud. Frozen fragments of the worlds that formed next to ours, kept in the cold of our backyard long after the siblings themselves wandered beyond our knowing. The family scattered, but the keepsakes remained, and there is something almost tender in that, underneath the vertigo. We tend to think of our solar system as an island, complete and separate, floating alone in the dark. But the picture emerging is of something more connected, more woven into the galaxy than we imagined. Our cloud may hold pieces of our stellar siblings and pieces of total strangers, material gathered from across the galaxy over billions of years and held in trust in the cold. The boundary between our system and the rest of the galaxy, which we always drew as a hard line, turns out to be soft, permeable, a place of slow mixing and quiet exchange. We're not as alone as we thought, and we're not as separate as we thought. The dark between the stars has been quietly trading with us the whole time. That, in the end, is the realization the title was reaching for. Not a monster in the dark, not a threat falling toward us, but something far harder to hold in the mind. The discovery that the empty space around our sun is not empty, was never empty, and may not even be entirely ours. That we live in the middle of a structure we cannot see, made partly of our own beginning and partly of elsewhere, so large and so old that everything we have ever done fits inside a single one of its slow breaths. To sit with that is not to be afraid. It is to feel, all at once, how small we are, how recent our knowledge is, and how astonishing it is that we have learned any of this at all. The terror and the wonder turn out to be the same feeling, looked at from two sides. And that is what astronomers mean when they say the Oort Cloud is not empty. They do not just mean that it has objects in it. They mean that it has turned out to be a place with structure, with history, with chemistry, and possibly with pieces of the wider galaxy folded into it. a place that holds questions we did not even know to ask a decade ago, and answers we're only beginning to learn how to translate. The dark around us is full. It has always been full. We simply had to build the instruments sensitive enough to begin to hear it. And once you have heard it, even a little, the sky never looks quite as empty again. Part 10. The world that made the theory real. For most of the time, the Oort Cloud existed only in equations. The part of it nearest to us, the inner edge, was the most theoretical piece of all. We could reason that comets fell in from the far outer reaches, but the inner boundary, the place where the familiar solar system fades and the great shell begins, was pure inference. And then, in 2003, a team of astronomers found a single small world that made that inner edge suddenly, startlingly real. Its discovery is one of the clearest examples I know of a place stepping out of theory and into the catalogue of actual named things. The world is called Sedna, named after an Inuit goddess of the sea, and it was discovered by a team led by Mike Brown at Caltech, working with Chad Trujillo and David Rabinowitz. Sedna is small and distinctly reddish, its surface coloured by the slow work of radiation on ancient ices over billions of years. But its colour was not what made it extraordinary. What made it extraordinary was its orbit, because Sedna goes places nothing else we knew of went. At its closest approach to the Sun, Sedna is already far beyond the Kuiper Belt, around 76 times the Earth-Sun distance out, and from there it swings outward to nearly 940 times that distance before it turns and falls back. A single orbit around the Sun takes Sedna roughly 11,400 years. The last time Sedna was as close to the Sun as it is now, human beings were just beginning to develop agriculture at the very dawn of civilization. That orbit puts Sedna in a category of its own. It is too far out to be a normal member of the Kuiper Belt. The planets cannot reach it. Neptune's gravity does not govern it the way it governs the closer icy bodies. But it is also far too close in to be a member of the main distant Oort Cloud, the source of the long-period comets. Sedna lives in between, in a region that, until it was found, had been purely theoretical. And the best interpretation we have is that Sedna is a member of the inner Oort Cloud, the near innermost layer of that great surrounding shell, a region we had reasoned about but never confirmed. With Sedna, the inner edge of the cloud stopped being a line in a model and became a real, reddish world with a name and an orbit and a colour. It was the first inner Oort Cloud body we had ever found, and we found it almost by accident, simply by looking carefully enough at the faint, slow-moving objects at the edge of the known. Since then, a handful of other bodies on similarly enormous orbits have turned up, and together they have begun to sketch the shape of that innermost layer, the boundary zone where our familiar solar system gives way to the frozen archive beyond. And the James Webb Space Telescope has been turning toward these objects too, building chemical portraits of Sedna and its kin, the same way it reads the falling comets. Slowly, the near edge of the cloud is being mapped, not as a theoretical surface, but as a real population of real worlds, each with its own composition, each marking the threshold of the great dark shell. There is a deeper mystery hiding in these distant worlds, and I want to mention it carefully, because it is a place where honest science and wild speculation sit very close together. The orbits of Sedna and some of the other most distant bodies seem, to some astronomers, to be subtly clustered, tilted and aligned in a way that might not be random. And one possible explanation for that clustering is the gravity of an undiscovered planet, far out beyond everything we have catalogued, quietly shepherding these distant worlds. This is the idea you may have heard called Planet 9. I want to be clear about its status, because it is easy to get swept up in it. It is not a confirmed object. Nobody has seen it. It is a hypothesis, a genuine and respectable one, proposed to explain a pattern that may or may not turn out to be real once we have surveyed enough distant bodies to know. It might be a real planet. It might be a statistical fluke of the small number of objects we have found so far. The honest answer is that we do not yet know. and the same surveys that are about to transform our study of the whole cloud are exactly what will settle it. I bring up Sedna and its mystery here for a reason that goes beyond the individual world. Sedna is a reminder that the map of the cloud starts at its inner edge, at the boundary of what we can already reach, and works outward into the unknown. We did not begin with the far reaches and move in. We began at the threshold, with the first body that proved the inner edge was real, and from there the map grows outward, one discovery at a time. Every new distant world we find, every comet we read, every orbit we trace, extends the chart a little further into a region that, not long ago, was nothing but a guess. Sedna was the first foothold on the near shore of the Great Dark, and the work since has been the slow, patient business of pushing the shoreline outward. Sedna did not stay the only one for long, and that matters, because a single strange object can be dismissed as a fluke, but a population demands an explanation. In the years after Sedna, astronomers found other bodies on similarly enormous detached orbits, worlds that, like Sedna, never come anywhere near the planets, and yet do not reach the far cloud either. Each one is desperately hard to find, because they spend almost all of their immensely long orbits too far away and too faint to detect, becoming visible only during the relatively brief stretch near their closest approach. Finding even a handful of them means there must be a great many more out there, unseen, in the parts of their orbits where they are simply too distant to catch. The inner edge of the Oort Cloud, it turns out, is not empty either. It is populated by a whole class of these detached, distant worlds, of which Sedna was simply the first we happened to notice. These worlds are the most accessible members of the Great Cloud, the near shore of the immense dark, and so they are some of the most valuable objects we have for understanding it. The same instruments that read the falling comets can study these bodies more carefully, because they are, in cosmic terms, relatively close and relatively steady, not flaring and fading like a comet, but sitting there to be examined. Reading the surfaces and the chemistry of Sedna and its kin gives us a way to probe the inner cloud directly, rather than only through the comets that fall from the far reaches. They are the foothold, the part of the great unknown that we can actually reach out and study in detail, and from that foothold we reason outward into the rest. The clustering of their orbits, the subtle alignment that some astronomers see in the most distant of these bodies, is the kind of clue that science lives for, and also the kind that demands enormous caution. It might be the fingerprint of an unseen planet, far out beyond everything we have catalogued, its gravity gently herding these distant worlds. Or it might be an illusion, a pattern that looks real only because we have found so few of these objects so far that chance alignments are easy to mistake for design. The honest position, the one the careful researchers hold, is that we do not yet have enough objects to know, and the only cure for that is more data, more distant worlds found and tracked, until the pattern either sharpens into proof or dissolves into coincidence. Which brings us at last to the machine that is about to provide exactly that flood of new data, and to transform our slow, patient study of the cloud into something far closer to a real survey. There is a puzzle hidden in Sedna's orbit that connects it directly to everything we have been saying about the wider galaxy, and it is worth drawing out. Sedna's path is strange, not just for being enormous, but for never coming close to the planets at all. Normally, when we find an object on an unusual orbit, we can trace that orbit back to a gravitational shove from one of the giant planets, usually Neptune. But Sedna never comes anywhere near Neptune or any other planet. Its closest approach to the Sun is far beyond their reach, so the planets cannot have placed it on the orbit it has. Something else must have, something from outside the ordinary machinery of the solar system, and the leading explanations all point outward, to influences from beyond our own planetary family. One possibility is that a star passed close to the Sun, long ago, and its gravity lifted Sedna onto this detached, distant path. Another is that Sedna was placed where it is during the Sun's crowded infancy in its birth cluster, when other stars were near and their gravity could reach in. And a third possibility, the most provocative, is that Sedna's orbit is shaped by something still out there, some undiscovered body whose pull we're reading in the alignment of the most distant worlds. Each of these explanations ties Sedna's lonely, beautiful orbit back to the same themes we have been circling all night: the influence of other stars, the legacy of the Sun's lost siblings, and the unmapped reaches still waiting to be charted. Sedna is not just the first foothold on the inner cloud. It is a small, reddish piece of evidence that our solar system has always been in conversation with the galaxy around it. That patient business is about to change scale dramatically, and this is where the story turns to look forward. Because everything we have talked about tonight, every comet read, every distant world charted, has been done more or less one object at a time, as chance delivered them. But we are on the edge of an era in which the objects will arrive not one at a time but by the thousands, and the slow sketch of the cloud will start to become a real map. The instruments that read the comets are about to be fed by a new kind of machine, one that will scan the entire sky again and again, catching the faint, slow messengers as they fall, faster than we have ever found them before. What that means for our understanding of the cloud, and for that simple, strange sentence about not being alone in our own backyard, is where this story finally comes to rest. Part 11. Learning to Listen. I want to be honest with you about what comes next, because it is not what a story like this usually promises. What comes next is going to be slow. We are not, in the coming years, going to get a photograph of the Oort Cloud. We are never going to get a photograph of the Oort Cloud. The distances are too enormous, the objects too cold and too faint and too far apart, and no telescope we can imagine will ever capture that great surrounding shell in a single image. If you have been waiting, through all of this, for the moment where I tell you we finally took its picture, I have to tell you that moment is not coming, and it never will. What we have instead is something stranger, and I have come to think it is something better. What we have is a way of listening, and that way of listening is about to get far more powerful, not because the telescopes that read the comets are changing, but because of how the comets will be found. High in the mountains of Chile, a new observatory has begun to work, the Vera Rubin Observatory, and it is going to do something no instrument has ever done before. It is going to photograph the entire visible southern sky, over and over, every few nights, for 10 years. And every time it does, software will compare the new images to the old ones and flag anything that has moved or changed. It is, in effect, a machine for catching the faint, slow messengers as they fall, and it is expected to discover new long-period comets not one at a time, the way we always have, but by the thousands. Think about what that does to everything we have talked about tonight. For 75 years, the study of the Oort Cloud was limited by how rarely a messenger arrived and how few we could catch. Each comet was precious precisely because it was so rare. Now imagine thousands of them, found and tracked and waiting, each one a candidate for the great infrared telescope to turn toward and read. Each one a fresh sample of the cloud's chemistry. Each one another data point in a portrait that, until now, we have been sketching from a mere handful of examples. By the early 2030s, astronomers expect to have read enough of these falling visitors to begin doing something genuinely new. Not studying individual comets, but characterizing the cloud itself statistically by region. Asking whether one part of the shell differs from another. Asking whether the inner cloud is chemically different from the outer. Asking whether there are zones loaded with carbon and zones loaded with water, whether there are clumps or gaps or anomalies in the great distribution. Asking, with real data, how much of the cloud might be foreign, captured from other stars. Picture a night a few years from now in the mountains of Chile. The new observatory is doing what it does every clear night, sweeping its enormous camera across the southern sky and then doing it again and again. Somewhere in the flood of images, the software notices a single faint dot that was not there 3 nights ago, a smudge moving slowly against the fixed stars. It is nothing to look at, just a few pixels of light against the black, but the path it traces marks it as a long-period comet, freshly fallen from the far cloud, perhaps making its first approach to the sun in millions of years. An alert goes out, and within weeks the great telescope a million miles from Earth turns quietly and takes that faint thread of light and fans it into a ribbon of colour and reads the chemistry of one more messenger from the dark. The map of a place no human will ever reach gains one more point, one more voice added to the chorus, one more sentence in a description we are writing of somewhere we can never go. That is the work of the coming decade. Not a single triumphant image, but a patient, accumulating map made of fingerprints instead of pictures, a chemical atlas of a place built entirely from the rare letters that fall out of it. We are making a map of a place no human will ever physically reach, and we are making it the only way it can be made by listening, one comet at a time, and writing down what each one says. I told you, at the very beginning, that this was the story of how the most distant region of our own solar system stopped being a guess and started becoming a place. I want to close by showing you just how far that journey has come, because I think it is one of the quietly astonishing achievements of our age. For most of human history, the Oort Cloud was unimaginable. It was not a place, not a hypothesis, not even a question. It was simply nothing, a dark we did not know was there. Then, in a single insight in 1950, it became a guess, reasoned into existence from the paths of falling comets. Then it became a name, and now, in just the last few years, it has begun to become a region of real study, with named worlds, measured chemistry, and a growing library of knowledge about what it actually is. Within a single human lifetime, an entire region of our own solar system has travelled from unimaginable to a guess to a place. Someone alive today watched that happen. You are alive while it is still happening. And the James Webb Space Telescope, the instrument at the centre of all this, did not do it the way the headlines say. It did not photograph the cloud. It will never photograph the cloud. What it gave us is stranger and, in the end, more useful. It gave us a way of hearing. Every comet that falls toward the sun is a single voice from a place we will never visit, carrying word of the early solar system, and possibly of other stars entirely, and we have finally built the ear to listen. We are learning, comet by comet, fingerprint by fingerprint, to hear a place that has been speaking to us in its rare and patient way for as long as there has been anyone to listen. There is a phrase I've come back to in thinking about all of this, and it is the idea that we are finally learning to hear a voice from the dark. When I first said it, early tonight, it was almost a figure of speech. By now I hope it has gathered some real weight. Each comet that falls toward the sun is, in the most literal sense, a single voice, carrying a message about the place it came from, written in the chemistry of its ice. For 75 years we could see those messengers but not truly hear them. Now we can. And the work of the coming decades is quite simply to listen to as many of those voices as we can, and to write down patiently what they tell us, until the chorus of them adds up to a description of a place no human will ever set foot in. It is a humble kind of greatness when you think about it. There will be no single moment of triumph, no famous photograph, no flag planted. There will only be the slow accumulation of knowledge, comet by comet, year by year, the chart of the cloud filling in one faint point at a time. It is the opposite of the dramatic discovery we are taught to expect. And yet what it is building toward is one of the most ambitious things our species has ever attempted, a map of the largest and most distant structure belonging to our sun, drawn entirely from the rare letters that fall out of it. We are mapping a place we can never visit by listening to the few of its residents that come to us, and trusting that, given enough of them, the shape of the whole will emerge. That is what it means to say the Oort Cloud is not empty. It is not a slogan, and it is not a scare. It is the plain result of finally building an instrument patient and sensitive enough to hear what was always there. The cloud went from nothing to a guess, to a name, and now, in our own lifetimes, to a place with chemistry and structure and history, and possibly with pieces of the wider galaxy folded quietly into it. We did not photograph it. We learned to listen to it. And that, in the end, may be the more fitting way to come to know the dark that surrounds us, not by looking, but by listening, until the silence we always assumed was out there turns out to have been full of voices all along. So let me leave you where we started, with that simple sentence, the one that I asked you to hold lightly at the beginning. We're not alone in our own backyard. When I said it then, it might have sounded like a turn of phrase, a bit of drama. I hope now it sounds like what it actually is, which is a plain description of what we have found. The space around our sun, the dark we used to think of as empty, is full of structure, full of history, full of frozen worlds that have been waiting in the cold since before the Earth was finished forming, and some of which may have come from stars we will never name. The void was never a void. It was a place, and it was full, and it was always there, surrounding us on every side, older and stranger, and more crowded than we ever imagined. The only thing that was ever missing was an instrument patient enough to hear it. We finally built that instrument, and now, when you look up at the dark, you can know that it is not empty at all. It is listening back,